Okie doke. So in this second installment, we're going to look at more advanced kind of thoughts and processes going on in energy levels and energy level diagrams with electrons. So I've pre-drawn an energy level diagram here. This is specifically for hydrogen. Okay, so these are the energy levels that electrons can sit in or reside in whilst they are in the hydrogen atom. So what we've got is a number of energy levels. Now, the thing about the energy level diagrams is you need to be wary of the fact that this almost seems backwards than what we showed you in the previous video. So in the previous video, I showed you that there was a number of energy levels, and I called it 1, 2, 3, 4, etc. And I said that the electrons jumped up that energy level and they absorbed the energy. And when they came down those energy levels, they emitted it. And that's exactly the same process that's going on here. If I have an electron that resides at this level right here, then what effectively this is saying is that it needs to gain the difference in the two energy levels in order to get there. So this minus is kind of like, is what we call a potential. It's like a potential well. It's how much energy it would need to get to zero. So it needs 13.58 electron volts. That's a unit of energy, electron volts. If you're not sure what an electron volt is, please do go look back at some previous videos to find out more about that. But it's just for all intents and purposes, is a very small unit of energy. And so this is saying that in order for this electron to get to zero, i.e. it's been ionized, and you may remember this from kind of GCSE level science, that ionized means that the electron no longer has anything to do with the atom. It's been completely released. So at level 0, it's no longer there. It's no longer a part of that atom. The nucleus of the atom has no longer got any kind of bearing on it. It's considered to be like at infinity. So it's been ionized at energy levels, this energy level here, 0. But at this first energy level, we call this n equals 1. And then obviously n equals 2, n equals 3, and these are energy levels going up. And so this does follow the same convention that we talked about here, but just not quite in the same way. So this is the amount of energy that, this is kind of the lowest energy level. This is the bottom of the pile right here. This is a very low energy electron. And so what can happen is if a photon of light with enough energy comes in, let's say around about 10 electron volts, there and thereabouts, it can then jump up that level by absorbing that that photon of light and going up to that next energy level. Obviously, if one comes in with, say, 12 or more, it can then get to higher energy levels, but it will only absorb very specific ones here. It will only absorb the amount of energy exactly that will allow it to go from there to there. Okay, so if it's too much or too little, it won't go. So if it's the exact amount, then it will absorb it and it will get up. That's why I've said this is a roundabout value. Obviously, it's the exact difference between those two. So, and in exactly the same way, electrons can jump up and jump down. So say we have an electron all the way up here at this top energy level here, super high energy, n equals 5, yes, n equals 5, then that electron could drop down all the way down to there and give off an amount of energy as a photon. And that amount of energy that's given off is the difference between the two energy levels. So in this case, what, 13.04. So 13.04 is the energy of the photon that's given off. Well, for the most part, what we've got here is we need to then consider how we can look deeper at these photons that have either been absorbed or emitted. And there's an equation for them. And hopefully you'll have come across the equation already, but you might not have appreciated its purpose, is that the energy of a photon is equal to hf, where h is Planck's constant and f is the frequency. And it's likely you'll do an experiment, or if you've not already done it, the Planck's constant experiment, where you can determine Planck's constant from a number of LEDs and looking at them in a dark tube when they just turn on. So this is a really nice equation because it then tells you, because Planck's constant is a constant and the amount of energy is given off is the energy of this photon, then we can work out the frequency of the light that's given off or absorbed in each case. So we can work out what frequency of light has been absorbed. So F is equal to E over H. And that's really useful because light all travels at the same speed, 3 times 10 to the 8. And so from your from stuff we've done in waves modules, V is equal to F lambda, or C in this case. So therefore we can actually also work out the wavelength of the light that's been given off, as lambda is equal to V over F, where V is 3 times 10 to the 8 over the frequency. And so, since that's a constant for the speed of light, so we can work out lambda. Well, we can actually almost change this equation to make another version of it in the first place. We can change it to be E is equal to hc over lambda. And that's just the speed of light from down here. So hc over lambda, well, we've just kind of put this equation, we've swapped out lambda in this case, sorry, we've swapped out the f for a variation of what it is in terms of c and lambda. So we have two very nice equations which allow you to work out exactly what light has been given off and exactly what light has been absorbed, which is really nice and really useful. And this the application of this is in astronomy, because when we look at stars, we can, and we'll talk about this more when we study astronomy, we do some astronomy videos, the application of this is that when we look at certain stars, we can see emission spectra where electrons are being dropped down energy levels and they're giving off certain wavelengths of light, or they might be absorbing energy levels which is blocking certain wavelengths of light. And as a result of that, we can actually then say what stars are made out of, because if we were getting this photon here or this photon here being blocked or emitted, then what we can say is that there is some hydrogen in this star, because this is the hydrogen energy level diagram. So we'll look at more and more applications of this later on, and we'll see how it goes, but we'll put these equations into practice as well. So just to remember that the energy that's given off, the energy of the photon, is equal to the difference in the energy levels that the electron changes between, and that will also be the same for absorbed photons as well.